Hello, I'm Keita Tokuda from Tsukuba University. Today I would like to talk about our attempt to predict student performance in Abacus-Based calculation using matrix factorization techniques. This work was conducted as a collaboration with David Kaschub, Takuma Ota, Yasunobu Hashimoto at DIGICA, an edtech company in Tokyo, and Naoya Fujiwara at Tohoku University, and Akihito Sudo at Shizuoka University. So this is the outline of the talk today. Firstly, I would like to introduce the iPad application for the Abacus-based calculation. That is how we acquired the students' learning history data of calculations. I would also like to give a brief introduction on the matrix factorization technique for user modeling and why we chose this approach in analyzing the educational data we had. Then I'll talk about the model and experimental results and conclude the talk. So the Abacus is a calculating tool, and it has been used for thousands of years, at least in East Asia. This is how the Japanese abacus, or Soroban in particular, looks like. And Soroban is a quite familiar tool among Japanese people. It is also included in the curriculum of the compulsory elementary schools. Soroban is made of multiple vertical columns with freely moving beads attached on them. It is designed to represent integers with the positions of the beads in an intuitive way. This is an example of the representation of the number 38 by Soroban. The beads are counted when they are shifted towards the horizontal beam at the center. Three lower deck beads shifted toward the horizontal beam represent the number 3, and the upper deck bead represents the number 5. Altogether, they represent the number 38. It is widely known that an advanced learner of Soroban is able to mentally calculate at remarkable speed and accuracy. The calculations shown here are the examples describing the level of the student at DIGICA aim to attain. So mentally calculating these operations within 10 seconds at age of 5 to 8. So we believe that learning Soroban is a means to acquire a remarkable ability in mental arithmetic calculation. What we like to achieve additionally here is to incorporate the data-driven approach in the education of Abacus-based calculation so that we can predict each student's performance more accurately and characterize each student's strength and weakness more precisely and realize automated adaptive curriculum based on data. However, it may not be an easy task because the progressions of the learning status of students may be a complex process. So development of an appropriate method for estimation of each student's learning state should be an important issue. However, to the author's knowledge, the data-driven approach has not been adopted in education of the abacus yet. One of the reasons that has hindered the data-driven approach in education is the lack of large data. We have previously reported an educational system developed by DIGICA called SoroTouch, which enables learning abacus-based calculation on iPad. As you can see, a student can conduct abacus-like calculation on SoroTouch by changing the position of the beads on the touchscreen. The data of detailed operations of a student on this application is recorded in the cloud server in real time, whenever and wherever the student uses it. As a result, this system has accumulated students' learning history data of hundreds of thousands of times of calculations so far. So we could use this data for the student modeling. As the algorithm for the student modeling, we use the matrix factorization technique, which has been very successful in user modeling, especially in the development of recommendation systems for entertainment, such as movies. As many of you may know, matrix factorization is a mathematical procedure to decompose a given matrix into two matrices. Let's assume the matrix on the right-hand side contain the data of the students' performances. Specifically, the st element of the matrix has the value of the student performance in the tth task. Then, matrix factorization, or MF, aims to approximate the matrix by a product of two matrices on the right-hand side, one consisting of the latent distributed representations of each student, and one consisting of the latent distributed representations of each task. Once you acquire the latent vector for a given student and for a given task, respectively, you can estimate the unknown performance of that student in that task by calculating the inner product of the vectors. As in the problem of characterizing human preferences in entertainment such as movies, it is expected that student state in learning calculation should be represented by multiple latent factors. For example, a student might have his or her strength in addition and weakness in subtraction, but another student may have his or her strength in subtraction, but in weakness in summation. So similarly, task in calculation could be also represented by multiple factors, such as the number of addition and subtraction, and the carry-ups, and so on. The advantage of MF is that it infers a distributed representation for each student and each task without detailed prior knowledge about how to construct the latent features. So next, I would like to move on to the model and experimental results. So this is the specific MF model we utilized in this study. In this model, the estimated performance of the S student in the tth task is expressed by a summation of 4 terms, namely the global average term and the student bias term, which takes a specific scalar value for each student, and the task bias term, which takes a specific scalar value for each task, and the student-task interaction term, which is denoted by an inner product of the vectors. The illustration below shows how the same equation can be described with the summation of 4 matrices. So the baseline method we used in this study are the 2 models, as in the former studies. One is the global average model, which takes only the first term in the MF model. And the second one is what we call the BUI model, as in the former studies. That takes the first 3 terms, the bias terms, and omits the interaction term. So this is the objective function we used in the optimization process, which is very in common way. So it consists of residual sum of the squares and the regularization term with Frobenius norms of the yielding 2 matrices. In this study, we use the value k equal 150, which is the dimension of the latent space, and beta equals 10 to the negative third, which is the regularization parameter. For the quantification of the student performance, we utilize the percentage of the correct answers. Namely, the st entry of the matrix was calculated by the ratio of the number of the correct answers the S student gave to the tth task to the total number of the answers the S student gave to the tth task, multiplied by 100. In order to discard noisy data, we have conducted a pre-processing, and we discarded any data of a student who solved less than 10 different tasks. And we also discarded data of any task that has been solved by less than 10 different students. And we also discarded any student task pairs with NSD total less than 40. As a result, we obtained a matrix with the dimension 2442 by 626. The number of the pairs where the data is given is 115,250 223, which is the 7.54% of all the elements of this matrix. The randomly chosen 95% of these points were used as the training data, and the remaining 5% were used as the test data. So this is the result we obtained with our analysis using MF model. The left scattergram shows the predicted values of the performances of students by the model in the test data, plotted against the true values. As you can see, there is a clear correlation between the model prediction and the true values. The right bar graph depicts the comparison of the model performance to the baseline models. The root mean squared error values, or RMSE values, calculated with the predictions in the test data are compared between the MF model and the baseline models. As you can see, the MF model outperforms the baseline models, suggesting that the MF model successfully acquired latent factors that determine the interaction of students and tasks in calculations. So this is the conclusion of our current study. Thank you very much for your attention.